Assalamualaikum and very good morning everyone. So today we will present our video presentation for subject SHAM 260 with the title of Gas Chromatography that will be prepared for Miss Nur Sandra binti Nurdin. So without wasting any time, let's go. So first and foremost, chromatography is a technique used to separate and analyze chemical mixture. In gas chromatography, which is CG, an inert gas carries the vaporized sample to a column, where a compound separates based on their interaction with stationary phase. Each compound is detected and identified by its retention time, while peak areas allows quantitative analysis. In this experiment, we use GC to identify components in a standard mixture and unknown sample, and to study how temperature affects separation and resolution. Next, let's dive into the objectives. The first one to determine the retention time of N-butanol and 2-propanol. Next, to identify the components present in the standard mixture based on the retention time. The third one to identify the components present in unknown sample. Last but not least, to determine the effect of temperature on the retention time and resolution.
This slide shows the fully labeled block diagram of the gas chromatography instrument used in this experiment. First, the carrier gas such as helium or nitrogen is supplied from a gas cylinder. The gas passes through pressure regulators, traps, and flow controllers to ensure a clean and constant flow throughout the system. The liquid sample is then introduced into the system using a syringe through the injector. The injector is heated to rapidly vaporize the sample before it enters the column. The vaporized sample is transported by the carrier gas into the GC column, which is placed inside a temperature-controlled oven. Separation occurs in the column based on differences in volatility and interaction with the stationary phase. After separation, the components exit the column and enter the detector, which in this experiment is a flame ionization detector. Hydrogen and air are supplied as fuel gases to generate a flame, and ions produced during a combustion are detected. The detector signal is amplified, converted into digital form, and then processed by the data system. Finally, the results are displayed as chromatogram showing detector response versus retention time.
Now, let's move on for the results. First, this chromatogram shows the result for 2-propanol at 70 degrees Celsius. From the chromatogram, we observe a dominant peak at approximately 2.72 minutes, with an area percentage of about 99.98%. This indicates that the injection sample is actually highly pure, with only a very small minor peak likely due to impurities or background noise. Next, this chromatogram shows the result for N-butanol at the same column temperature at 70 degrees Celsius. The main peak appears at a longer retention time of approximately 5.84 minutes, with an area percentage of about 99.85%. Compared to propanol, butanol has a longer carbon chain and a higher boiling point, which increases its interaction with stationary phase. As a result, it remains longer in the column before eluting. Now, this clear difference in retention time allows us to later identify each compound in the standard mixture. Moving on, this chromatogram represents the standard mixture analyzed at 70 degrees Celsius. Now, two major peaks are observed. The first peak appears at around 2.69 minutes, which closely matches the retention time of propanol. The second major peak appears at approximately 5.9 minutes, which corresponds to butanol. Now, the identification of each compound is done by comparing the retention time of the unknown peaks with those of the individual standards analyzed earlier under the same conditions. Therefore, the earlier eluting peak is assigned to propanol, while the later peak is assigned to butanol. Now, when the column temperature is increased to 100 degrees Celsius, we observe that both peak elute earlier compared to 70 degrees Celsius. The retention time decreases because higher temperature increases the vapor pressure of the analytes, allowing them to move faster through the column. However, although analysis time becomes shorter, the peaks begin to move closer together, which may reduce resolution if the temperature is increased too much. At 140 degrees Celsius, the retention time decreases even further, with peaks appearing much earlier. At this higher temperature, separation becomes faster, but peak resolution is reduced, and minor peaks may become less recognizable. This shows that while a higher temperature improves analysis speed, they may compromise separation quality.
Next, I will discuss the result of the gas chromatography analysis. Gas chromatography successfully separated the alcohol compounds based on their volatility and interaction with the stationary phase. Clear peaks were observed for propanol and butanol, showing effective separation. The compound in the unknown sample were identified by comparing their retention times with the standard mixture. Propanol eluted earlier due to its lower boiling point, while butanol had a longer retention time because of stronger intermolecular interactions. Column temperature influenced the result, where higher temperature reduced retention time but lower resolution, while lower temperature improved separation with longer analysis time. Therefore, an optimum column temperature is required for efficient analysis.
In this experiment, we successfully used gas chromatography to separate and identify alcohols, specifically propanol and butanol, by comparing their retention times with a standard mixture. We observe that column temperature plays a critical role in both retention time and peak resolution, meaning that setting the right temperature is essential for accurate analysis. Overall, all the objectives of the experiment were achieved, demonstrating that gas chromatography is a reliable technique for analyzing volatile organic compounds.